Dear students, good morning. Today we'll continue the nuclear chemistry class. See, it is the lecture number 5. Okay, under nuclear chemistry, today we'll discuss nuclear instability. So, nuclear instability means it is the unstable nature of nucleus. Unstable nature of nucleus. Okay, now why the nucleus becomes unstable? So, what is the reason? And if it becomes unstable, what happens further? Okay, those things we'll study today. Okay, now basically you are well familiar the symbol of any atom of an element. It is given by XZA. Okay, so Z indicates it is the atomic number of that element, and the Z indicates those many number of protons are present and equal number of electrons are present in that atom. And A stands for, here A stands for the total number of protons plus neutron. Okay, so that is said to be mass number, or the number of neutron can be calculated. A minus Z is equal to number of neutrons, N. So this is, you are familiar. Okay, now suppose Z equal to 1. Say it is a hydrogen atom. So 1 H1. So what it indicates? Here Z equal to 1. That means hydrogen contains 1 proton, 1 electron. So A is equal to 1. A minus Z is 0. That means there is no neutrons in hydrogen atom. So if you come to the helium, okay, it is 2 helium He raised to 4. So what this indicates? Helium contains 2 protons, 2 electrons and 2 neutrons, because 4 minus 2 is 2 neutrons. Now the next element, say sodium. So atomic number is 11 and mass number is 23. So here the sodium contains 11 proton, 11 electron and 12. 23 minus 11 is 12 neutron. Okay, we'll go to the next element. Say we'll take iron. Atomic number is 26 and mass number is 56. So now this indicates the iron contains 26 protons, 26 electrons and 30 neutrons. This minus this gives you 30 neutrons. Okay, similarly, if you take one more example, say zinc. Atomic number is 30. Mass number is 65. So the zinc contains 30 protons, 35 neutrons. Okay, so if you take the example, say lead, Pb. Okay, so which contains 82 protons and 82 electrons, and 207 minus 82 gives you 125 neutron, and this itself is the stable heaviest naturally occurring element. This itself is stable nucleus, that means stable heaviest element with atomic number 82. And further above this, that means 83 or onwards, they are not stable. Okay, yes. So now what is the reason for unstable nature of, say, nucleus? Now the protons at the nucleus, say the size of the nucleus you are well familiar. It is in the order of 10 raised to minus 15 meter. The diameter of nucleus is in the order of 10 raised to minus 15 meter. Okay, so now say in such a small fraction of volume, okay, as the atomic number increases, the proton enters the nucleus. So if it is 1, only 1 proton is present. If it is 26 protons are present in this small volume. So if it is 82, there are 82 protons. Now protons are positively charged particles. You are well familiar. So the like charges repel each other. Therefore, the positively charged particles, for example, in case of helium, so if there are 2 protons entering the nucleus or present in the nucleus, then there is a force of repulsion between those 2 protons. Similarly, when there are 26 protons, then there is a still greater forces of repulsion arises among the protons, all the 26 protons. Suppose 30, there are 30 protons in this small volume. and all the 30 protons, they are repelling with each other among themselves, isn't it? So force of repulsion increases as the atomic number increases, because proton number increases and all protons are positively charged particles. Okay, and at the same time there is an increase in number. See here, in helium it is 2 neutron, and in sodium there is an increase. Say 11 proton, 12 neutron. And if you come to iron, 26 proton, 30 neutron. In zinc, 30 proton, 35 neutrons. So in lead there are 82 protons, and number of say neutrons is almost double. Say it is nearly 125 neutrons are present. It is 1.5 times greater, okay, than this. So as the atomic number increases, that means as the number of proton increases, at the same time number of neutrons are also increases rapidly. So now when the protons number increases, the nucleus is expected to be unstable, but the presence of neutrons which holds all the protons together, that means the number of neutrons provides a short range forces of attraction and which holds all the protons together. That means the number of neutrons, see, the presence of greater number of neutrons offsets. It offsets or it compensates or it overcomes the forces of repulsion among the protons, thereby it holds the nucleus stable. Okay, suppose if the nucleus becomes unstable, what happens? It starts radiating, that means disintegration it undergoes, and such elements are said to be the elements which are having unstable nucleus. They are said to be radioactive elements, and once it is a radioactive element, it starts undergoing decay or disintegration or radioactive decay. That means it emits the particles like alpha, beta, gamma, etc. So how long it radiates? Till it reaches the stable nucleus state or stable nucleus. Okay, so now you are familiar why the nucleus is, say, unstable, why it becomes unstable, and why later how it becomes stable till the atomic number 82. And further, there is an increase in 83, 84, 85 onwards, there is an increase in proton and there is also an increase in neutron, but after 83 or above, it is difficult to say offset or to overcome the force of repulsion among the protons which are present at the nucleus, and thereby, so after above 82 atomic number or 83 onwards, the nucleus is say unstable and it is a radioactive element. Therefore, so the any element its atomic number is greater than 82, it is considered as a radioactive. Therefore, naturally occurring highest or heaviest element is lead, which is stable, which has a stable nucleus. Okay, so now the stability or the instability of nucleus can be explained on the basis of two factors. So one is N by P ratio. So this figure, it indicates, okay, so N by P ratio. So this graph, so when you draw the number of neutrons versus number of protons, that means atomic number up to 20, say up to 20 atomic number, say the number of proton is equal to number of neutron. So number of proton ratio to neutron is 1 is to 1, or say proton to neutron. Proton to neutron ratio is 1 is to 1. But above 20, so atomic number above 20, say the ratio increases. This ratio increases and it reaches maximum of 1.5, and that is almost in case of say lead. Okay, so now, so if you draw the graph N versus P, and I think you are familiar with the word isotopes. So isotopes means what? So isotopes are the elements or which are having the same atomic mass, atomic number, and different atomic mass. So I will give you an example. Say carbon. Say carbon 6, 11, carbon 6, 12, carbon 6, 13, carbon 6, 14. So these are said to be isotopes. These are said to be isotopes of carbon. Is it? Isotopes of carbon. So means what? All carbons are containing same number of proton but different number of neutrons, and these are said to be isotopes. So there are many elements which exhibits many number of, say, 2, 3, 4, say isotopes are exhibited by the elements, and by taking those elements, all the isotopes of the elements, and when you draw the number of neutrons present in them versus number of protons, up to 20 the ratio is 1:1 and they are quite stable, and further say the ratio is increases from 1:1 to 1:1, 1:1.5. It increases 1:1, 1.5, 1 is to, so there is an increase. There is an increase. So now say the elements which are falling, and this is said to be a line of stability, or sometimes it is also referred as a band of stability or belt of stability. So, okay, this line indicates it is the line of stability or belt of stability or the region of stability of isotopes, okay, or for stable isotopes. Now the elements which are falling below, that means right of this line, so they are said to be which are having more number of protons and less number of neutrons. So thereby they undergo positron emission of positrons or alpha radiations, and thereby they decrease the proton number and they increase proton will be get converted into neutron. And those elements which are lying left or above or left to the line, they are said to be unstable, and they reach the stable line or they enter this stability belt by emitting beta minus particles, okay, beta particles. So thereby somehow they are achieving the stable isotope state, okay. So as the n number increases, stability is also increases, and that is corresponding, that means there is a relation between n and p. And similarly, say the stability of the nucleus can be explained by taking one more, say the graph. When you draw, you are familiar with binding energy per nucleon. So greater the binding energy, greater will be the stability of the nucleus. See here, when you draw the binding energy per nucleon versus mass number, say it is seen that, say it increases, say when you draw the graph of binding energy per nucleon versus mass number, there is an increase in ratio, that means there is an increase in stability as the mass number increases, and it reaches highest at iron 56, and iron 56 where the binding energy per nucleon, say in this case you have seen in the last class you have calculated, nucleon is 8.812, it is the highest, 8.812 MeV, mega electron volt is the binding energy per nucleon in case of iron, and this is the highest. And after, say from this graph we can say as the binding energy increases, the stability of the nucleus is also increases, and after 56 or above 50 it remains almost, say, flat. That means even there is an increase in mass number, that means increase in number of protons or the binding energy, increase in mass number, but the binding energy per nucleon almost remains same. So thereby it becomes flat, and almost they are quite stable, those which are having the binding energy in this range. So now these are the two factors with which one can explain the stability of nucleus, okay. So we'll discuss in the next class. Thank you.